Today is the day we learn about lesson 10.1, which is called Recursive Formulas. It's obviously the first lesson in chapter 10. We are going to have to look at some new terms that we will use throughout the chapter. So it's an introduction to the chapter and then also about recursive formulas. So first of all, we are going to define sequences. Before we do that, we do a quick review of relation. So a relation is a set of ordered pairs. The x value is the first element in the ordered pair. Your x value goes there and your y value goes there. If you have a bunch of points, your domain is the set of x values and the range is the set of y values. A function is a relation, so it is a set of ordered pairs in which each element in the domain, so each x value, is paired with a unique element of the range. So each x value goes to only one y value. So a sequence is a function, so it has a domain and range, and each x value is paired with only one y value, in which the domain is the set of whole numbers. So the domain is 1, 2, 3, 4, 5, and it keeps going. The domain is the set of whole numbers. So since we know what the domain is already, we don't always list our sequence as a set of ordered pairs. We just list the sequence, and whatever term is in the sequence, that one goes with the corresponding x value. So, denoting terms in a sequence, the range are denoted a sub n, where n corresponds to which term in the sequence you're referring to. So a sub 1, so a sub n is the term of the sequence, which means a sub 1 is the first term, a sub 2 is the second term, a sub 3 is the third term, and a sub n is the nth term, which is sometimes we use just generically. So, here's a couple questions to look at. How would I indicate the sixth term? Well, if it's sequence dealing with a, now we don't always have to use a, by the way, but here we are. So a sub 6, the 20th term, a sub 20, the 54th term, and hopefully this is pretty easy by now, the 61st term, we could say a sub 61, and a sub 120. That's the term. That's how we can indicate it. So actually this tells us the 20 tells us our domain value, and then a sub 20, whatever number that is the range value. All right, what's the second term? Well, here's the first term, and there is the second term. The second term in the sequence is 6. What is a sub 5? Well, that is referring to the fifth term. 1, 2, 3, 4, 5. That's our fifth term, which is 33. 77 is which term? Hey, I found 77 here. It's 1, 2, 3, 4, 5, 6, 7. It's the seventh term, so we put a sub 7. And which number corresponds to the domain value of 3? Well, there are no domain values written here, but we recall that the domain is just the natural numbers. And so this 8 here really represents the term 1, 8, 2, 6, 3, 9. So the one that corresponds to the domain value of 3 is 9. So we don't often write the domain, so sometimes we forget, but it is a function. All right, so that function that sequence we just talked about, 8, 6, 9, 21, 33, 45, 77, 1, 4, really has no pattern to it. So not really all that interesting to us, but most of the sequences that we study have patterns, and that is why we study them. So let's find the next three terms in the following sequences. So what we'll want to do is we'll want to determine what the pattern or the rule is, and then we can find the next few terms. So 2 to 9. I mean, usually the first thing we do is figure out, is it adding the same thing? This is adding 7. Adding 7, adding 7. So the sequence follows the pattern that you just keep adding 7. 23 plus 7 is 30. 30 plus 7 is 37. And 37 plus 7 is 44. Next one. Let's try it again. 3 plus 9 is 12. If we add 9, it would be 21. Our pattern is not adding 9. Next, we'll try multiplying. 3 times 4 is 12. 12 times 4 is 48. 48 times 4 is 192. So 192 times 4. 192 times 4 is 768. Times 4. It will take 768 times 4 is 3,072, and times 4 is 12,288. 768. So this was 768, 3,000 something, 72. And I should have remembered this one as well, but I did not. 12288. 12288. So that one was multiplying by 4. Next one, 1, negative 1, 1, negative 1. Well, this seems easy enough. We just keep changing between 1 and negative 1. This is an important sequence. How can we get from this mathematically? So we added 7, we multiplied by 4. Is there a mathematical way or using operations to get to the next term? Well, we can multiply by negative 1. But we can just look at the pattern and see that it keeps alternating 1 and negative 1. But realizing that multiplying by negative 1 does change the sign of the term. It will alternate signs, positive, negative, positive, negative. All right, moving on, understanding the order of terms. These are going to start off simple, but there is an important thing that sometimes we lose track of. So what is the term right before a sub 6? So right before the 6th term is the 5th term. That's a sub 5. It's right before it. What's the term right before the 39th term, or a sub 39? Well, that is a sub 38. What is the term right before the nth term? What comes right before n? Well, right before 39 came 38, 1 less than 39. Right before 6 came 5, so right before a sub n is a sub, and n minus 1 is in the subscript. You want to go right before it, so you subtract 1 from it. What term is 2 terms before a sub n? Well, you want to go 2 terms back, you subtract 2. Again, it's in the subscript. Do not write it like this. This is taking your nth term and then subtracting 2. That is different. This is referring to the term 2 before a sub n. And what about the term right after a sub n? We want to go to the next one. Well, that's a sub n plus 1. That'll get us to the next term because we go up by 1. We're in the natural numbers. So these three are good to understand, that you're 1 before, 2 terms before, and a term right after. All right, so that was our preliminary information. Now we're going to look at recursive formulas. A recursive formula, recursive formulas express a term in the sequence using previous term or terms. So find the first 5 terms using the following recursive formulas. When stating a recursive formula, you must always state at least 2 things. you have to state the formula and a term. We usually state the first term. So down here, these three sequences, our A sequence, the B sequence, and the C sequence, these are recursive formulas. They state an equation or a formula, and they state, in this case, the first term. I see I have a typo here. This should be C sub 1. All right. Find the first 5 terms. First term goes right here. Well, that's easy. It is 4 because it says it's 4 right here. The next term, I'm going to try to zoom in and write a little bit smaller here. So our first term was 4. Our second term, and this is where we need to be able to figure out this notation. We don't always need it, but our second term, we're going to use this formula. Our second term is equal to 3 times a sub n minus 1. A sub n minus 1. Well, we're talking about n being 2. So a sub n minus 1 should be a sub 2 minus 1. So our second term is 3 times the first term. And what's the first term? First term was 4. So 3 times 4 is 12. So we have 12 here. I'm taking this a little bit slow just so we understand how these terms work. I've had times in the past where we struggled with this notation. The third term. Well, according to our formula, which I'll write because I went off, the nth term is always equal to 3 times, and I like to call this the term before it, because it is the term before it, but a sub n minus 1. So the third term is going to be 3, because that's our formula, times, and so the third term is going to be a sub 3 minus 1. So our third term is 3 times the second term. So 3 times the second term, which was 12, which is 36. So the third term is 36. And once we know the third term, that can help us find the fourth term. A sub 4 is 3 times a sub 4 minus 1. But this 4 minus 1, I don't always want to have to think of it that way. I can think of the term before it. So the third term, and I don't even always want to write that. I should just be able to think, well, that's 3 times the term before it, which is 36. 3 times 36 is 108. And to find the fifth term, we're going to take the fifth term, or we're going to find the fifth term, which is 3 times the term before it. So I'm not going to write this whole thing out again. I'm going to say, what's the term before it? The fourth term, which is 108, and that multiplied together is 324. So understanding a sub n minus 1 just means the term before it. So as long as we have a formula, and where we're supposed to start. We had to start at 4, and then it was easy from there. Next one, our B sequence is B sub n is B sub n minus 1. So the term before it, minus 2. Well, our first term is defined. We have to have a starting point, so 3. Our second term is going to be the term before it minus 2. So a sub 2 is going to be the term before it. What's the term right before the second term? That's the first term. So 3 minus 2. That is 1. The third term is going to be the second term, the term before it, which was 1 minus 2, so negative 1. The fourth term is going to be the term before the fourth one, which is the third one, so negative 1. And we're still subtracting 2. And the fifth term is going to be the term before the fifth term, which is the fourth term, which was negative 3. Subtract 2. Next one. Ooh, let's take a look at this. Our C sequence is defining our first term. Let's go to a different color. We'll do this one in blue. Our first term is -2. And what it tells us here, I'm going to leave ourselves a little more room. Our second term is going to be the term before it. So I'm going to go back to this notation, cubed. So our second term is simply going to be our first term cubed, which is -8. Our third term is going to be the second term, which was -8 cubed. -8 cubed, which I believe is 512, -512. And then -512 cubed. Don't know that one. So -512, I'll just do 512 because I know that's going to be negative. Cubed 134217728. Ooh. 134217728. 7728. Whoa, now I'm supposed to cube that to get my fifth term. We're going to go ahead and stop there. Actually, don't even know that the calculator will do that. Let's see, it might. So we want that answer cubed, and it put it in, if you see that e to the 24th, it put it in scientific notation. So that's 2.417851639 times 10 to the 24th. It's a very large number, so we're not going to worry about that. But those are using recursive formulas, and once again, in order to write a recursive formula, you need the formula and a term, usually the first term. Notice how all these gave us the first term. All right, this time, so I have a definition of recursive formula still there. Recursive formulas express a term in the sequence using previous term or terms. State the recursive formula for the following sequences. Remember, you need two things, the equation and the first term. So these are the ones from before. This one we kept adding 7, if you remember. So we had 30, 37, 44. Well, what's happening to get the nth term, to get some term in there, we're taking the one right before it, which we write a sub n minus 1 in the subscript. And again, be careful when you write this. Make sure your -1 is in the subscript. And what are we doing to the term before it? We are adding 7. So there is our formula. But the problem with just having a formula is we don't have a starting point. So we need to define one of the terms, and we usually define the first term. So the first term is 2. That gives us our starting point, and once we have our starting point, we can add 7 to each term to get the successive terms. Let's call this next one D. So D sub n. We kept multiplying by 4 here. Kept multiplying by 4. And so, even without these 3 terms here, we can figure this out. We take the term before it and multiply by 4. But once again, that's great and all, but we need a starting place, so we are going to define our first term, which was 3. Once we have a first term, we multiply by 4 to get 12. Then we take the second time, multiply by 4 to get 48. This last one kind of indicated what was going to happen here. But how do we keep switching from +1 to -1 to +1 to -1 to +1 to -1? Let's call this K sub n will equal the term before it times -1, or actually we can just put the opposite of the term before it, which is great. We see that the keep going opposites. Opposite of positive 1 is negative 1, but then the opposite of negative 1 is positive 1, and then opposite again. But we need a starting point, so we define our first term as 1, and then the rest of the formula works out. All right, let our first term be 1 and our second term be 2, and our nth term always equals the term right before it times the term two things before it. For n equals, so we're starting at 3, 4, 5, because we've already defined our first two terms. Well, we've already have first and second. We want to find the third. Well, the third term is equal to a sub 3 minus 1 times a sub 3 minus 2. You don't always have to write this work once you start understanding what this means. I'm just showing you that these subscripts actually do work out. They mean something. So 3 minus 1 is 2. That's this one. Times 3 minus 2 is 1. So we actually really want the second term times the first term. So the second term is 2 times 1 is 2. That's our third term. Our fourth term is going to be defined as the term right before it. Remember that subscript of n minus 1 means the term right before it. So what's right before the fourth term? It's the third term. What's 2 before the fourth term? The second term. We're going to multiply those. The third term we found was 2. And the second term was defined up here. That was also 2. So the fourth term is 4. How do we find the fifth term? The fifth term, let me erase some stuff here and kind of start afresh. The fifth term is going to be equal to the term right before it, which that's the fourth term, times the term 2 in front of it, the third term. So the fifth term is the fourth term times the third term. The fourth term was 4. The third term was 2. So our fifth term was 8. So there we go. In that case, we had a recursive function, recursive formula. And in this case, we had to define two things. They gave us two things, the first two terms. All right, give a recursive formula for this sequence. So we might need to know what's happening first. So we see 2 to 4, 16 to 56. Well, we don't want highlighter. 2 plus 2. 2 plus 2, is 4, but plus 2 is not 16. So adding 2 doesn't work. Okay, let's try times 2. 4 times 2 doesn't give 16. That doesn't work. Well, maybe you recognize these terms as this is something squared, this is something squared, and this is something squared. So for this one, it looks like you want to take the term before it. So 2 squared equals 4. 4 squared equals 16, and 16 squared equals 256. So we want to take the term before it, which we put a sub n minus 1. And what do we do to the term before it? We square it. There's our formula, but we need our starting point, so we define our first term as 2. It's not that hard to define our first term. It's written right there. Here are some special sequences that we will see throughout this chapter. So not just this lesson, but the entire chapter, especially these first two. An arithmetic sequence is its consecutive terms differ by a constant. Each term is obtained from the previous term by adding the same constant called the common difference, and we call it D, the common difference D. So we always take the term before it and keep adding the same number. We saw a couple of those already in examples where we had it was equal to term before it plus 7, I think it was, and we had to define our first term, I think might have been 2. So that was an arithmetic sequence when you keep just adding the same thing to get the next term. So if you have a name for adding the same thing, so this term is important, common difference. If you see common difference, you know it's referring back to an arithmetic sequence. Well, sometimes you add the same thing to get the next term. Well, maybe we should multiply. So a geometric sequence, the ratio of consecutive terms is constant. So that's helpful. The ratio is constant. The way that we can write the formula is we use the common ratio R. That's if you have the ratio of the maybe second over first. But you take that ratio and multiply it to get to the next term. So we take, to get the nth term, we take the term before it and multiply it by R. We had this as well. I think we started with 3 and we multiplied by 4 to get 12, and then we took 12 times 4 to get 48, and then we took 48 times 4 to get 192. That's a geometric sequence. We keep multiplying by the common ratio. And notice that if we took the 48 divided by the 12, you would get that common ratio of 4. Those are the two most common. Next, we look at the Fibonacci sequence. That's adding the two previous terms. So in this case, you're going to have to define the first term and the second term. But we haven't seen one like that yet. We multiplied the previous terms, but we haven't added. So that's named after a guy named Fibonacci. There's some interesting patterns and things that you can find out with Fibonacci sequences. Factorial. This one's interesting, and we'll see more about this when we talk about our formulas in the next lesson, explicit formulas. But what you do is you take the term before it and multiply by what term you are on. And we usually define a sub 1 as 1. So to get a sub 2, we're on the second term, and we multiply it by the one before it. So 2 times 1, which does equal 2. The third term, we take 3 times the one before it, which I'm going to write it still as 2 times 1 so you recognize what's happening here. To get the fourth term, you take the term you're on, which is 4, and multiply it by the one before it. So 3 times 2 times 1. And so it ends up like the seventh term is 7 times 6 times 5 times 4 times 3 times 2 times 1. And so that's the factorial. And then the last one is a harmonic sequence, and that's the reciprocal of an arithmetic sequence. This formula looks a little funny, but it will give you a harmonic sequence. For an example, a harmonic sequence might be 1/2, 1/6, 1/10, 1/14. And notice I just keep adding to the denominator 4. But in order to do that, you actually take the reciprocal of the term you're on. So let's just put a 1/2 in here. Put a 1/2 in here. Well, 1 over 1/2 means the reciprocal of 1/2, so that's 2. So this whole thing is 2 because the reciprocal. We add that common difference of 4, because I mentioned 4, they go up by 4. And you get 6, so that's 1/6. All right, last example. Give the first 5 terms of the sequence if you start with 1/3. Well, this does look like what we just talked about, but let's plug things in to see what happens. So our first term is 1/3. Our second term is supposed to be 1 over, that's this there, the previous term, so 1/3, plus 5. Well, this just means the reciprocal of 1/3, which is 3, plus 5 is 1/8. Okay? Our third term is 1 over the previous term plus 5. I'm going to this formula is what we're using. Well, this is the reciprocal of 1/8, so this is 1 over 8 plus 5 is 1/13. So let's notice our pattern here. What keeps happening? Well, we keep adding 5 to the denominator. So our fourth term, once we find the pattern, we don't have to use the formula anymore. That should be 1/18. And then the fifth term, add 5 again, 1 over 23. And what type of sequence it was this? Well, that was the harmonic. That was the last one we saw. And there is your lesson on